In section 3.9, we will talk about the derivatives of logarithmic and exponential functions. This is kind of a long section, so we'll split it up into two parts in 2 days. And the first day will consist of the derivatives of exponential functions. So we will take a look at two types of exponential functions, one where the base is e, and another one where the base is any other integer, but not e. So we can see the formulas here. The one we'll be using the most is this second one, which is d dx of e to the u equals to e to the u times du dx. And the reasoning behind that is when you take the derivative of u with respect to x, in other words, the input variable and the term are different, we get that du dx. We'll be also using this second formula here quite often, which is d dx of e to the u, where a is an integer that's not e. That's going to equal to a to the u times ln a, where a is the base, times du dx. And we get that du dx because we're taking the derivative of u with respect to x. So the term and the input are different. Okay, so our first example, we want to take the derivative of x to the 6th times e to the 6.5x. So our a is going to be the first term, which is x to the 6th, and our b is going to be the second term, which is going to be e to the 6.5x. Now on the side, let's write down our a prime, b prime. A is x to the 6th, so a prime should be easy. It's the power rule of derivatives, so the 6 comes down, we get 6x to the 5th. Now for b, we have e to the 6.5x. Now notice that the exponent is not x, it's another function. So we're going to be using this second formula, which is e to the u times du dx. So the e to the u stays the same, but you have to multiply by the derivative of the exponent. So the e to the 6.5x stays the same, but as you can see up here, the derivative of the exponent, which is 6.5x, is equal to the 6.5, so that du dx is going to be 6.5. And again, anytime your exponent is not x, it's something else, you also have to multiply by the derivative of that exponent. So once we have that, we know it's going to be b times a prime plus a times b prime. So we have our b, which is e to the 6.5x, times a prime, which is 6x to the 5th, plus our a, which is x to the 6th, times our b prime, which is going to be e to the 6.5x times 6.5. Next example, we want to find the derivative of 5e to the negative 6x to the 8th minus 9x to the 10th. So this exponent is going to be the u term. So our u is going to be the exponent or the parentheses that's going to be negative 6x to the 8th minus 9x to the 10th. So when you have a u, you always need a u prime. And if you use the power rule of derivatives, we get negative 48x to the 7th minus 90x to the 9th. So the derivative of e to the u is just equal to e to the u times u prime. Now we know what u is, we know what u prime is, we just plug those in. Okay, e to the u, that's e to the negative 6x to the 8th minus 9x to the 10th. And then u prime is negative 48x to the 7th minus 90x to the 9th. And then finally, we have to move this parentheses to the front so we can distribute the 5. So that moves to the front. We multiply the 5 to the parentheses, and that gives you negative 240x to the 7th minus 450x to the 9th times your e to the u, which is e to the negative 6x to the 8th minus 9x to the 10th. Okay, next example, we have 3 to the negative 4y plus 9. So notice we have a y instead of an x, but that doesn't make a difference because we're still taking the derivative of y with respect to with the u substitution. So we have the formula we're going to use is a to the u, and you take the derivative of that is going to be a to the u times ln a times du dy. Now why do we have a different formula? Well, in the first two examples, our base was e. So if your base is e, we're going to use the first set of formulas. But if your base is a, then we're going to use the second formula, a to the u times ln a, where a is the base, times du dx. Okay, so in this example, that's exactly what we have. So our base a is 3, and our u is negative 4y plus 9. So on the right, I'm going to put my u, which is negative 4y plus 9, and then my du, which is going to be negative 4. So let's plug everything in. We have a to the u, so that stays the same. 3 to the negative 4y plus 9 times ln of a, ln 3, that stays the same. And then all we have to do is we just have to multiply by du dy, which is the derivative of the exponent, and that's negative 4. And if I rearrange it, this becomes my final answer. All right, so the next example is going to be a little bit different. And here's why it's different. So in the previous example, our base was 3, an integer. In the previous example, our base was e, which is a constant. But here, we don't have a constant as a base. Our base is actually x. So what do we do? So notice that this is not a to the u, because a must be a constant, and that's not what we have. Okay, so what we're going to do is we're going to take this x to the 8x, and we're going to have to find a way to get that 8x down and make it a coefficient. Now, if you think back to your college algebra or pre-calculus class, the way we can do that is first you set this equal to y, the term y, okay, and then we take the natural log of both sides. The natural log of y and the natural log of x to the 8x. Now, why do we do this? Because there's a property that if you have the natural log of x to the 8x, where 8x is the exponent, that exponent comes down, and that only happens for natural logs. So we're going to get our natural log ln y equals to 8x times ln x. Okay, now in the previous section, we talked about the derivatives of natural log of y. Okay, so now what we're going to do is we're going to take the derivative with respect to x of both sides, of the left and the right. Now the right side, we have a product rule. We have 8x times ln x. Notice we have the product rule, 8x times ln of x. Okay, so what happens when you have the product rule? Well, our a term is going to be 8x, so our a prime is 8. Our b term is going to be ln of x, and the derivative of that is going to be 1 over x. So that's a formula where the derivative of ln is just 1 over x, 1 over that term. Okay, now let's take the derivative of ln of y. So because we have y with respect to x, we're going to follow this formula where the derivative of ln x is equal to 1 over x. So in this case, it'll be 1 over y, but we're going to have that dy dx. We have the dy dx. Why do we have that? Because we're taking y with respect to x. Okay, then we have our right side, which is our product rule. So our product rule is going to be b times a prime. So our b is ln x times a prime, which is 8, plus a, which is 8x, times our b prime, which is 1 over x. And then the x's cross out, so these go away, and we're left with 8 ln x plus 8. And on the other side, we still have the 1 over y dy dx. So let me rewrite that. So I have 1 over y dy dx, and that's going to equal to 8 ln x plus 8. But we just want to get that dy dx by itself. We don't really care about that y. So we're going to multiply both sides by y in order to get rid of that y and get the dy dx by itself. So we're going to have dy dx equals to y times 8 ln x plus 8. And then lastly, we know what everything has to be in terms of x, not in terms of y. We know that y equals to x to the 8x from the original term. So we're now going to replace the y with x to the 8x, so everything can be in terms of x. And this is going to be our final answer. Now you probably have questions about this, and that's completely fine. Please come to class prepared with questions, and I'll be happy to answer them for you. So the next part will be done in the next video. And here, once again, we look at this formula where the natural log of x has a derivative of 1 over x, and the natural log of u, where the term is not x, is equal to 1 over u times u prime. And that's what we used for that previous example. But again, we'll get to it in the next section.